Every physicist uses the laws of nature every single day. Almost none of them ask why there are laws at all. I find that strange, because the question, why the universe is governed by consistent mathematical laws rather than arbitrary chaos, may be the most important question in physics, and it sits just outside what physics currently knows how to answer. The usual response when the question is raised is something like, the laws are just there. That's how things are. Asking why there are laws is like asking why words mean what they mean. The question dissolves on examination. Laws are descriptions of behavior. Of course, behavior can be described. What's the mystery? The mystery is this: a universe without laws is physically conceivable. A universe where particles behaved randomly, where the same initial conditions produce different outcomes each time, where no consistent relationship between cause and effect held across time or space. There's no logical reason such a universe couldn't exist. It just isn't what we observe. We observe a universe that follows consistent mathematical rules to extraordinary precision. The question of why it does that, rather than something else, is real, and it currently has no complete answer. Let me show you how deep that question goes. Start with what a physical law actually is, because most people have a picture of it that isn't quite right. The common picture: a physical law is a rule that nature obeys, a constraint imposed on matter and energy. F equals ma as an instruction to particles. When a force acts on you, accelerate proportionally. The electron consults a Schrödinger equation and behaves accordingly. Laws as commands. This picture is wrong, and the error matters. A physical law is a mathematical description of a pattern in observations. It summarizes what has been consistently observed to happen and predicts what will be observed next. The law doesn't cause anything, it describes. The pattern of behavior is the thing. The equation is the description of the pattern. When Newton wrote his law of universal gravitation, that masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, he wrote a description. An extraordinarily precise, extraordinarily successful description. For over 2 centuries, it predicted planetary orbits, the motion of cannonballs, the behavior of tides, with accuracy that astonished his contemporaries and continues to astonish anyone who thinks carefully about it. But the law doesn't explain why masses attract each other at all. It doesn't explain why the force falls off with the square of distance rather than the cube, or linearly, or in some other way. It describes the pattern. It doesn't explain why the universe has that pattern rather than a different one. This is a precise distinction. Knowing the description is not the same as knowing why the description is correct. Physics has been extraordinarily successful at finding descriptions. It has made much less progress on the question of why the descriptions are what they are. In 1960, Eugene Wigner published an essay that physicists have been discussing ever since. The title was The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The thesis is in the title. Mathematics is unreasonably effective. Mathematics is a human intellectual construction. Mathematicians develop formal systems through pure reasoning, exploring the properties of abstract structures, proving theorems about objects that may have no physical referent, following logical consequences of axioms to wherever they lead. The motivation is internal to mathematics: elegance, generality, the resolution of interesting problems, not physical application. And then, repeatedly, with a frequency that should strike you as extraordinary, mathematics developed for purely abstract reasons turns out to be the correct language for describing physical reality. Non-Euclidean geometry. In the early 19th century, mathematicians asked, what would geometry look like if Euclid's parallel postulate were false? If parallel lines could meet, or if the angles of a triangle didn't sum to 180 degrees. The question was purely mathematical. Non-Euclidean geometry was developed as an abstract curiosity, a logical exploration. Nobody thought it described anything physical. Then Einstein built general relativity. The mathematical structure of space-time, the geometry of a four-dimensional manifold with curvature produced by mass and energy, is exactly non-Euclidean geometry. The mathematical curiosity of the 19th century was the correct description of gravity. Complex numbers. Invented because some polynomial equations have no real solutions. Solutions require the square root of negative numbers which don't exist on the real number line. So mathematicians invented them, imaginary numbers, complex numbers. Considered for centuries as a formal trick, a useful fiction. Then quantum mechanics was developed. The wave functions that describe the state of every particle in the universe are complex valued, not approximately complex, exactly. The fundamental description of physical reality requires numbers that were invented because of an algebraic inconvenience. Group theory, the abstract mathematical study of symmetry, of transformations that leave certain properties unchanged. Developed in the 19th century with no physical motivation whatsoever. Then, the standard model of particle physics. The fundamental theory of particles and forces is a statement about specific symmetry groups, SU3 cross SU2 cross U1. Group theory is the language of the most precisely tested theory in the history of physics. Why? Why does abstract mathematics, developed without reference to physical reality, describe physical reality with such extraordinary precision? Wigner called it a wonderful gift which we neither understand nor deserve. It suggests a deep relationship between mathematical structure and physical structure that we don't currently have the conceptual framework to explain. And that relationship is at the heart of why physical laws are the way they are, because the laws are mathematical, and why they're mathematical is itself a mystery. The deepest thing physics has learned about where physical laws come from is this. The most fundamental laws are not brute facts. They are consequences of symmetry. Noether proved this in 1915, one of the most important theorems in all of physics, criminally under-recognized for decades because Noether herself was under-recognized. Noether's theorem states, every continuous symmetry of a physical system corresponds to a conserved quantity. This is not an approximation, it is a mathematical identity. A symmetry, in this context, is a transformation that leaves something unchanged. The laws of physics are the same today as they were yesterday. They don't change with time. That symmetry, invariance under time translation, corresponds, via Noether's theorem, to conservation of energy. Energy is conserved not as a brute fact, but as the mathematical consequence of the laws of physics not changing in time. The laws of physics are the same here as in a distant galaxy. Spatial invariance corresponds to conservation of momentum. The laws of physics don't depend on which direction you're facing. Rotational invariance corresponds to conservation of angular momentum. The conserved quantities that physicists measure and rely on, energy, momentum, angular momentum, electric charge, are not independent fundamental facts. They are shadows of symmetries. The symmetries are more fundamental than the conservation laws, and the conservation laws are more fundamental than the specific forces. The forces themselves, electromagnetism, the strong and weak nuclear forces, can be derived from a specific type of symmetry called gauge symmetry. Require that the equations of physics remain unchanged under certain local transformations that can vary from point to point in spacetime, and you're forced to introduce interaction fields. Those fields are the forces. Requiring a particular symmetry generates electromagnetism. Requiring a different symmetry generates the strong force. The laws of physics at their deepest level are statements about what doesn't change under what transformations. The question shifts. Instead of why do these laws hold, ask why does the universe have these symmetries? That question is deeper. Physics can derive many things from symmetry. It cannot yet explain why the universe has the symmetries it does rather than different ones or none at all. The laws of physics contain numbers, specific measured values, the fundamental constants of nature that appear in the equations and cannot be derived from the equations themselves. They must be measured, and they appear to be finely tuned. The speed of light, approximately 299,792,458 meters per second. The gravitational constant, the mass of the electron, the fine structure constant, approximately 1/137, that governs the strength of electromagnetic interactions. The cosmological constant, the energy density of empty space. These numbers are not derived from any current theory. They are inputs, and their values sit in multiple cases within narrow windows that permit the existence of complex structure. The strong nuclear force, if its strength were a few percent weaker, protons and neutrons wouldn't bind together in nuclei. No nuclei beyond hydrogen, no chemistry, no anything except hydrogen gas. If the strong force were a few percent stronger, all hydrogen would fuse to helium in the early universe. No hydrogen left, no water, probably no life. The cosmological constant. Quantum field theory predicts a value for the energy density of empty space. The predicted value, from summing up vacuum fluctuations of all quantum fields, is approximately 10 to the power of 120 times larger than the observed value. The observed value requires a cancellation between a bare cosmological constant and the quantum field contributions of extraordinary precision. 1 part in 10 to the 120. This is the largest discrepancy between theoretical prediction and observation in the history of physics. We have no explanation for why the cancellation is so precise. The fine structure constant, if it were significantly larger, electrons would be bound too tightly in atoms for chemistry to work as it does. If significantly smaller, atoms would be too large and diffuse for stable molecular bonds. The values of these constants appear to sit in a narrow region where complex structure, atoms, stars, chemistry, biology, observers, is possible. The question, is this coincidence? Is there a reason? Is there a deeper theory from which the values can be derived? Currently, no. The values are measured, not derived. No existing theory predicts them from more fundamental principles. The fine-tuning problem has generated several serious proposed frameworks. None is confirmed. Each is an honest attempt to push the question further. The multiverse. If the constants of nature take different values in different regions of a larger reality, if our universe is one of many, each with different physics, then it's unsurprising that we find ourselves in a region where the constants permit our existence. We could only exist in a region that permits us. The observed fine-tuning becomes a selection effect rather than a mystery requiring explanation. The problem? The multiverse is not currently testable. If other universes are causally disconnected from ours, they produce no observable evidence. A framework that explains fine-tuning by positing unobservable entities has a specific scientific status problem. It can't be wrong. A theory that can't be wrong isn't a scientific theory in the standard sense. Some physicists find this acceptable, others find it disqualifying. The mathematical universe hypothesis. all mathematically consistent structures exist as physical realities. The physical universe is one such structure. We exist in the structure that permits our existence. Fine-tuning is real, but not more mysterious than the fact that we don't live in a desert. We live where the conditions support us. The problem? This is a metaphysical claim of vast scope with no clear testable prediction. It's philosophically interesting. It is not established physics. The possibility that the laws are uniquely determined, perhaps a final theory would show that only one consistent set of laws and constants is mathematically possible, that any other values lead to mathematical contradiction. Some physicists have hoped string theory would deliver this. Current evidence? String theory appears to have an enormous landscape of possible solutions. Perhaps 10 to the power of 500 distinct possible sets of constants, rather than a unique prediction. This is the opposite of what was hoped. None of these escapes is satisfying. All are honest. The question remains open. Let me say the thing that I find most important about all of this. The universe operates according to laws, consistent mathematical, symmetry-based laws. Those laws produced hydrogen, which formed stars, which produced heavier elements, which formed planets, which produced chemistry, which produced biology, which produced nervous systems, which produced something capable of discovering those laws, expressing them in the language of mathematics, and asking why they exist. The laws are being examined by something the laws produced. There is something genuinely strange about this. The existence of an entity capable of asking, why does the universe have laws, is not independent of the answer. Any universe without consistent laws would have no stable structures, no atoms, no chemistry, no observers. The question can only be asked from inside a universe where the answer permits the questioner. This doesn't explain anything. It describes a relationship between the existence of the question and the nature of the answer that is, I think, worth noticing. I have spent my career looking for beautiful equations. I have believed, and continue to believe, that the most fundamental laws of nature take a mathematically beautiful form. The equation that bears my name is beautiful in the specific sense I mean. It is compact, symmetric, it treats space and time on equal footing, it contains within it consequences, antimatter, electron spin, that were not put there deliberately. The beauty was a reliable guide. The equation was right. But I cannot tell you why mathematical beauty should track physical truth. I cannot tell you why mathematics describes physics at all, rather than being an interesting internal game with no external referent. I cannot tell you why the universe has the symmetries it has, or why the constants have the values they do, or why there are laws rather than arbitrary chaos. These questions sit just outside what physics currently reaches. Not because physicists haven't tried, because the questions require a framework that doesn't yet exist, a theory deeper than the standard model, deeper than general relativity, deeper than any theory we currently have, from which the specific laws and constants we observe could be derived rather than measured. That theory may come. Physics has surprised itself before. Quantum mechanics was not predicted by classical physics. Relativity was not predicted by Newtonian mechanics. The next framework may be as different from current physics as quantum mechanics was from what preceded it. What I'm certain of is this: the question is real. The universe being governed by consistent mathematical laws is not self-explanatory. The laws being these laws rather than different laws is not self-explanatory. The constants having values that permit complex structure is not self-explanatory. The universe operates by rules it didn't choose. Something discovered those rules. Neither knows why they're there. That gap between the laws and their explanation is where the next physics must live.